Hello, this is Dr. Michael Garut, Professor of Chemistry at Missouri Southern State University. I'm going to make a brief video on how to graph on graph paper. This is a good skill to have because it will help you to understand better when we graph on the computer or when you're trying to interpret graphs that are printed in some resource, what you're looking at. So these are some good skills to have. This particular graph paper is an image of the same graph paper I typically give out in class for this purpose. It's marked the large divisions in centimeters, and each centimeter is divided into 10 components, so that's tenths of a centimeter or millimeters. If you count them across, and I just zoomed out there a little bit so that you can see the whole paper, you'll find that there are 25 major squares or divisions along the horizontal axis. There are 19 along the vertical axis. And you'll also notice that I've put my paper in landscape orientation so that I have more room in the horizontal direction. That's typically how you see graphs in a landscape orientation. So you should definitely put your paper that direction. And again, there are 25 divisions along the horizontal and 19 along the vertical. And this is the data that you collected in class for the volume and the mass of those two plastic items. Perhaps you'll remember that our data looked something like this, and we are plotting the mass on the y-axis. We're plotting the volume on the x-axis, and when you determine the slope, that's the rise over the run. So that would be the grams over the milliliters, which is density. In the table, it's calculated the densities for each of the class readings, but we want to get an average density, and you'll also recall that there were two different solids. These 5 points here are one of the solids, and the remainder of the points are the other solid. So when you make a graph, you will have two lines. One straight line will try to do the best to go through these lower 5 points, and one through the rest of the points. We decided in class that the points should go through the origin, or 0, 0, because when you have no mass, you also have no volume. So that must go through 0, because by definition, if you have no mass, there's no volume. So you'll have two lines that both go through 0. Perhaps you'll remember that I showed in class some data from another class when we had more time and were able to collect more data. And in that class, you can also see that there are two sets of data, one with a line that is for the higher density and one with a line that's for the lower density. And then I used a computer program, Excel, to graph those data sets separately, and I put them in different colors, and so you have two slopes. Notice there is no intercept because you have the formula y equals the slope times x plus the intercept, but we defined the intercept to be 0, so therefore this number is the slope. That slope is the grams per milliliter, and therefore that slope is the density. So this class determined the density of one solid to be about 1.45 grams per milliliter, and this one determined it to be about 1.08 grams per milliliter. Our class results will probably be slightly different. One thing I want you to pay attention to is the divisions on the graph. Notice how they are in units of 5. That's a good scale. We would like our divisions on the graph to be factors of 10. So 1s or 2s or 5s or 10s, or going the other direction, 1/10 or 1/2, right? But not like 3 or 6 or 8.1 or any weird thing like that, because it helps us if we need to interpolate between the readings. We can do that because we're naturally used to doing things in factors of 10. And I even made that note for you here in this Google Sheet. Notes for graphing by hand. Use landscape orientation, which we're doing. The major divisions should be in factors of 10. And this new part, which is when you're doing it by hand, you want to make sure you choose a scale so that more than half of the page is filled up with your scale in both the X direction and the Y direction. I'll talk about that with the picture of our paper. So remember that we decided there were 25 horizontal boxes or centimeters, and there were 19 in this direction. If we know for sure that we need to start at 0 on both the y-axis and the x-axis, the x-axis is going to be the milliliters, and the y-axis is going to be the grams. Let's look at the grams first. The highest number of grams I see is 28.3, which is 2 different times. I don't see anything higher than 28.3. But I only have 19 boxes going vertically. If I took that 28.3 and divided by 19, I get about 1.5, which means you could do this in about 1.5 per centimeter, but 1.5 isn't a whole number factor of 10 or a reciprocal of that. If I used ones, I would only get as high as 19, so that's not enough. So how about if I round this up to 2? 2 is a factor of 10, and that would work. So then I could do 2, 4, 6, etc. So I've gotten up to 26. I'll go ahead and put 28 and 30. That's as high as I really need to go because I don't have any data that's higher than that. I will have satisfied my rules of using a factor of 10 as a scale, and also using up, by the time I get to 28, I will have used up more than half of that vertical distance. So I'm taking advantage of the full size of the graph paper as best as I can with the rules that I am constrained by. So now in the X direction, that's my milliliters, and the maximum number of milliliters looks to me like 19.6. And in this direction, I have 25 lines. So I think you can probably see that for that one, I can make each one be 1 milliliter, and it'll go all the way up to 25. The highest reading will be 19, and that will be a good scale. So if you wanted to check that, you would say, well, my highest reading is 19.6 milliliters, and I have 25 lines going, or divisions from left to right, and when I divide that, I get 0.78. All right, 0.78 rounds up to 1 if I'm trying to make it fit my rules. I could use 0.5, but if I use 0.5, I would only get up to 12.5, and that's not going to get me to 19. So I'm going to go ahead and put them in one at a time. I'll pause the video while I write those in. And again, when I put my largest value of 19.6, that will use up more than half of the scale in the X direction, so that's great. Which of these points are the ones that are the lower ones? You will be able to see when you graph it. It's going to be the 5 ones that are the lowest. However, when you look at the data, I think you can probably tell that a lot of these are around 1.3 to 1.5, but there are a few of them that are closer to 1. So, like this one. Those are the 5 that are going to be the lowest densities, and that will be one of your lines, and then the other one will be the other lines. We could, like we did in part 1, just average these numbers and get some statistics, but this is the second way of accounting for the random variation in our measurements. We call it measurement error, and by making a straight line, we're going to make that work out. Now we see why it's really helpful to put these in factors of 10. Let's just plot this first point. The volume is 19.0 milliliters, so that one's pretty easy. And the mass is 20 grams. That's also pretty easy because they're both right on the lines. So volume of 19 milliliters is going to be right on this line, and a mass of 20 grams is going to be right on this line, so that point is going to be right here. However, when they're not exactly on, so let's try 10.7 and 17.1. So 10.7 milliliters, well, I have a 10 and I have an 11, but there's little tiny marks there for each individual one. So 10.7, you'd count 7 of the little tiny divisions over. And then 17.1 for the mass, well, 17, since we have 2 between 16 and 18, 17 would be right smack in the middle. So now there's only 5 divisions between 17 and 18. So 17.1 would only be halfway from the middle line to the next line up. 16.2, 16.4, etc. So if I'm wanting to plot as a mass 17.1, well, the 17 is right smack in the middle, and I want to go over as far as 10.7. So there's my 10, and there's my 11. So let's make a plot that's at 10.7. So that's 7 lines over, and then 17.1, and that's going to be pretty close to right there. So that's another spot or plot. If you don't like the dot, then you could make an X. And then once you have all of your spots plotted, it should look right. You'll have, I'm just going to make up some points. You'll have some points that are the 5 lower ones, and then you'll have a bunch of other points that were the higher ones. And then, since you're on a piece of paper, you can get out a straight edge. It doesn't have to be a ruler. It could be just a textbook cover. If you don't have a ruler, I happen to have a ruler. And so I'm just putting the ruler so that the straight line will go exactly through 0 and try to get through the center of those 5 points, like so. There's my straight line. And then I would do the same thing for the other points. So trying to go right through the center of them and also through 0, 0, like so. Now I just made up most of these points, so those won't be the same as your line. But then we need to determine the slope. Now remember, when you determine the slope, you're determining the rise over the run. It's tempting to just use one of these points. But if you just use one of these points, you're just using one of these data points. We want the average of those, and the only way you're getting the average is by using the line that you've drawn, not any of the points. Since I have 0, 0, a formula for rise over run, you might remember, is going to be something like y2 minus y1 over x2 minus x1. That's the slope. But if y1 and x1 are both 0, because we forced it to go through 0, then that's just 0 and that's just 0, so you're left with just y over x. If you can find a place where your line goes exactly through one of these cross points, and better if it's over to the right of your graph, because that way you have larger numbers and you'll get a better error. That's why we wanted to use the whole piece of paper, right? We certainly wouldn't want to pick it right here, because then if I'm off by 1/10, that's going to change my slope by a lot. But if I'm off by 1/10 out of 20 something, that's not going to change by very much. So it looks to me like this line that I drew goes exactly through that point, which is 24 over 24. So that turns out to be exactly 1.0. Now, I don't think the density, I just remember I made up these points. I don't think the density was actually 1.0 because remember it sank in the water. So it has to have a greater density than 1.0 or else it wouldn't sink in the water. But that's what I got, 24, 24. And I would say the slope of this line is 1.0, and therefore that is the density of that solid, 1.0 grams per milliliter. The only thing I would need to do to finish my graph would be to put a good title on it, and there are some examples of that in the Google Sheet. So I think this gives you a good idea of how to make what we call a scatter plot, how to draw a best fit line, how to determine the slope of that line. That's it. Cheers.